Today on Applied Science, I'm going to talk about these e-ink or e-paper displays. These things are made popular in the Kindle and other e-readers, and now they're available on the hobbyist market, and you can play with putting them in all kinds of different projects. Of course, one of their signature features is that they retain the image even when it's not connected to anything at all, so it takes literally zero power to maintain the image. And of course, the look of it is much more like paper than it is a liquid crystal display. They also have these interesting red, white, and black displays, which are pretty cool. It's not a color filter. We'll talk about the tech that goes into these, but it's actually really unusual how these work. So the setup I have here today is a teensy microcontroller that we're programming through the Arduino interface, and it's driving this display over the SPI bus. You can see I bought this one from Waveshare. And then we have this glorious scope from Tektronix on loan from Tektronix to monitor the SPI bus. Waveshare is not a manufacturer of these panels, but they are I guess a distributor that also makes these breakout boards. So it's very convenient to have a board that converts the flat flex that's on the display to this a pin header. And also they provided some firmware, which is a great starting point. So let's zoom in on the display and check out some demos. Okay, I'm going to run the demo that comes direct from Waveshare. It's just 2 frames, and so it's compiling and downloading. And you'll see when the image transitions, first you see the inverse of it, then all white, then all black, then the image. This is the frame. And then it's going to switch back to the first frame, and as you can see, it's a pretty long process. So you can't change any part of the display without going through that entire multi-second refresh routine. And the early Kindle and other e-reader type things had this same characteristic to them. You can't just update the screen, you have to clear it entirely. However, if you know how to tweak the firmware, you can make the screen do anything you want. Actually, interestingly, the controller is very programmable, and it's sort of security by obscurity. You can load any values you want into the registers and cause it to do anything. You may hurt the display, but let's take a look and see what's going on. Okay, so I'm going to load up the demo reel that I made with my custom firmware, and we'll see how fast the update is. So the first one clears it, that's just a standard update. And now you can see the frame rate is about 3 Hertz. So we don't have to flash the whole display, and we can update any part of it within 1/3 of a second. This one shows what an animation would look like at close to 3 Hertz. And you can see that I'm drawing text up here, and I'm slowly moving the text in the X direction across the screen to prevent burn-in, which we'll talk about a little bit later. The ball going around in circle doesn't really cause much burn-in, but you will see if you look closely, there's a ghost image as it was going to a full white screen. So you can still see that ghost image. So now we'll go back to Waveshare. These are all full updates, as you can see, because it's going through the cycling. That should look familiar. You can see when it's done cycling, there's no more ghosts left, like the text is completely clean. When it's going through its image update process, you can see a little bit of remnant. So we'll talk about this a little bit more, but I think that the pulse sequence I've come up with is more or less safe, but it's possible that if you somewhat abuse the display like this, eventually there will be burn-in, permanent maybe. Certainly short-term burn-in for sure. Let's talk about how these things actually work, and then it'll make it clear why we have this problem with burn-in. So if we were to cut one of these displays and look at the cross-section from the side, we would have sort of a smooth top, which is an electrode, and we'll call that common. And then within the display there's a whole bunch of chambers, and these are not necessarily pixels, they're just little chambers within the display. And within each of those there are positive and negative particles, and they're submersed or they're suspended in a fluid, oil of some kind. And the trick is that the positively charged particles are black, let's say, and the negatively charged particles are white. So if we put an electrode array on the bottom, and in this case each one of these is a pixel, and if we put a positive voltage up here and a negative voltage here, the field will cause the negative particle to migrate to the top and the positive particle to migrate to the bottom. So what we'll end up with is white particles, if those are negative, going to the top, of this pixel. And then as we scan across, we can change the fields for each one of these pixels. Pretty cool. In its most basic form, you could just put one voltage across this thing, and if you're scanning through all the pixels, you could say, okay, you know, positive on top, negative on bottom for this one, positive on top, negative, and scan through it, and the display would work at least once or twice. But the problem is with electrostatics and fields like this, eventually the parts of the display will become charged themselves. And so if you keep putting this electric field on the display, eventually this positive charge will accumulate in the display, and then your display won't work anymore, because when you put a voltage on there, you're going to be fighting against all the charge that's in there. So one of the tricks to driving these things is you actually put an AC voltage on this and rapidly cycle it to prevent it from becoming polarized. There's actually a similar problem with LCDs. You can't run an LCD with just DC voltage because it will polarize and stop working. If you search around on e-paper distributor sites, you'll see that some of the newer displays are actually rated for what they call partial refresh. So basically doing this without any flashing or flickering, get a new image on the screen without any of that. And I think the trick is they've basically just loosened the sort of the usage restrictions. And so they're saying, okay, you can bend the rules a little bit by putting just a DC voltage on there to get a quick update, but then you better do a full refresh at some point near in the future. And I think, you know, the reason that it's hard to find instructions on how to do this is because they know that you're going to degrade the panel's performance if you don't have the right routine. So it takes a little bit of experimentation to get all this working. Additionally, this display that I'm using, this 4.2 inch, actually has 2 complete frame buffers inside of it. And so it knows, it keeps one frame buffer as like the currently displayed image, and then the other frame buffer is the image that it wants to display next. And what it does, it knows that if there's, if this pixel is currently white, then it knows that all the positive charge is on the top or whatever. And if it knows that it wants to convert that pixel to black in the next frame, it actually gives it a different sequence of positive and negative voltages than if it's going to stay white in the next frame. So the display has this thing internally called the Lookup Table, and it basically has a set of waveforms that we're going to put on these pixels, and the waveform is selected based on what the pixel was in the last frame and what the pixel is in the new frame. And it seems kind of overkill, but obviously they wouldn't go through all this trouble if it wasn't necessary. So coming up with this correct drive sequence is basically the secret to all of these e-paper displays. So what about these red ones? You might think, well, it's probably just a color filter. I mean, it's probably just white pixels underneath a red thing, but that's actually not what's going on. It's a true 3-color pixel. It can select whether it's going to be red, black, or white. And I searched around, and it took a long time to find this out. But I think the way it works is kind of like this. Imagine that you have black pixels that are small and positively charged, and then you have really large red ones that are also positively charged, and then you've got small white ones that are negatively charged. So then if you put this thing between the 2 electrodes, the large ones and the small black ones will have the same motive force applied to them. If we put this field here, minus on the bottom and positive on the top, both the red and the black will be attracted to the top, let's say, but the red ones are going to move more slowly because they are bigger, even though the charge is about the same, and it's in this viscous sort of fluid. So if you put a voltage on here quickly, the black ones will make it to the top faster than the red ones, and the pixel will turn black. If you want to turn the pixel red, what you do is you first make it black, so that you're in this configuration with the white ones in the bottom, the red ones kind of in the middle, and the black ones at the top. Then you switch the field, causing the black ones to move down and the white ones to move up. But before they have a chance to switch places, the red ones will actually end up being the ones that are closest to the top, and the black ones will be kind of below, and the white ones haven't started moving just yet. I think each manufacturer has their own special trick of how this works. And even searching patents and things, it's actually very difficult to figure out what's going on here. But when we start looking at the code, you'll see there's special pulse sequences to get the red ones to the top. It's amazingly effective. I mean, it's a very high contrast sort of display, and there's no, I mean, you can see the background is actually a little bit white compared to a black and white only e-paper, you can see the background on this one is much paler. It's much truer to white. This one's a little bit reddish, probably because those red particles aren't fully at the bottom. But nonetheless, it's a very cool look. Okay, let's take a look at the code that runs this thing and the changes that I've made to do this fast update. So the code from Waveshare is free and public domain, and so I've made some changes to it and am redistributing it on my blog. Check the description for links to all this stuff. And what it is an Arduino library and an Arduino demo sketch, so you can get the thing running. And so in libraries, it's going to be this EPD42 directory, and almost all of the work is done in EPD 4inch2.cpp. The sketch itself is pretty self-explanatory. I'll also include a demo, basically the same demo reel that you saw there, and it's relatively straightforward, especially if you've used LCDs from SparkFun or Adafruit before. Basically the idea is that you construct a frame buffer and edit the frame buffer by using these draw filled circle routines or put text in there, and then you send it to the display and tell the display to update, and some time will go by, about a third of a second. Wait until idle, and then you can do something else with the display. So pretty straightforward. So let's take a look at the CPP file from Waveshare. If you're new to editing C code at this level, it may look a little gnarly, but just stick with it. It's not too bad. I would recommend starting from the sketch and seeing what functions are being called here, and then tracking them down in EPD 4inch2.cpp. So you can see we've got EPD set partial window. So if we scroll through here and find set partial window, here it is. And I've modified the function slightly from the original Waveshare function, and I've added one new parameter called DTM, which is this data transmission mode. So I mentioned that the display has two frame buffers, one for the old image and one for the new image, and you can actually edit each frame buffer completely independently. So you can tell it whether you want to insert the new image or the old image. At first it doesn't seem to make much sense, but remember that the waveform that is being given to each pixel is determined by the difference between these two frame buffers. So if you power off your device, you can actually restore the old frame buffer from non-volatile memory so that your display always has the correct waveform. It's kind of a little bit unnecessarily complicated. You can basically just always assume that you're starting from a white display, or you could even write your firmware to always leave it in a white display state. It's kind of up to you. Anyway, the next thing that happens is display frame quick, so let's take a look at that. Here's display frame quick. It's pretty similar to the original display frame. The main difference being I've got set LUT quick here, and I've gotten rid of the just the delay commands. So let's take a look at the difference between set LUT in the original and set LUT quick. We'll scroll up. The command happens to be above it in the file. So the original set LUT uses these variables LUT vcom0 and LUT ww, and as you can see they have some descriptive names here, white to white, black to white. So this is the difference between frame buffers for each pixel. So it picks out a waveform from this lookup table for each of these pixel transitions. So the original set LUT just uses these variables, and I have like a parallel function that uses quick variable functions, or quick variables. And at the end of this file, I have all of this stuff written out. So let's start digging into what this is actually doing. Okay, so here we've got the lookup table on the left and the data sheet on the right that explains what all of these values do. And it was very difficult to find this data sheet. This is actually for the IL0373 controller, which is not the one used in the 4.2-inch e-paper display. If you start off with the correct data sheet, the 4.2-inch e-paper, and track down the controller that it's using, it's the IL0389, and all of the lookup table information has been removed from this data sheet because the industry thrives on secrecy or something. But luckily there aren't that many e-paper display controller manufacturers, and they happen to use the same lookup table format in a lot of different displays. However, it's not the same in all of them, and so you have to start poking around and lots of trial and error and whatnot. The thing that was the tip-off here is that these lookup tables are 42 bytes long, magic 42, and this datasheet spec'd 42 byte lookup tables, so I knew I was on the right track. Oh, I should point out that the WaveShare files came with this lookup table. That's how I knew it was 42 bytes, because there was in fact an original lookup table in the WaveShare files. However, funny enough, if you look through the code, the original code carefully, it doesn't use them. In fact, it even has a function called setLut, but it never calls the function. Or I think maybe it did call the function, but it didn't set up the display to use it properly. I'm not going to get into the super low-level details, but if you use my code, it works just fine, so just stick with that. There's actually a couple of really nasty typos in the original WaveShare code. Okay, let's take a look at what this thing's actually doing. You can read this thing left to right, top to bottom, just like a book, and the very first byte out of the sequence tells it what voltages you want to put on that specific thing. And if we look, you actually can control VCOM, which is the what we're calling the common electrode, the one that's shared among all pixels. So you can actually control that voltage. And if we go to the data sheet for VCOM, the lookup table for VCOM, that first byte selects 4 different voltages, and it can be VCM DC, VDH, VDL, or floating. The subsequent 4 bytes tell this thing how long you want those voltages to be applied for this part of the waveform. And it says number of frames. And so in this example over here, we've got hex 40 gives it the voltage values that we want. So we can come to our calculator here and say hex 40, that's 0, 1, 0, 0, 0, 0, 0, 0. So 0, 1 is VDH plus VCM DC. And then the next one is hex 17. So we'll try that. In decimal, it's 23. And as it happens, the frame rate is 50 hertz, and you can also change that through the things, but let's just say it's 50 hertz. So then 23 times 53 hertz gives you the length of time that voltage will be applied. In some of the other data sheets, they actually had a better graphical representation of this. So you can see this is kind of a little bit easier to see what's going on here. So out of all of these little bits and bytes that are put into that lookup table, you'll eventually end up with a voltage waveform that's applied to the pixels, and that's what makes this whole thing tick. So let's take a look at the original lookup table versus my lookup table. So here's white to white original and white to white quick. So you can see the original one is actually pretty complicated. It's a hex 40, which is the voltages we're going to apply, then it's 17, which is the time that the voltage is going to be on, and then this 5th byte is actually, or 6th byte is actually the number of times to repeat that whole part of the sequence. So this is voltage 40 times 17, repeat it twice. Then it does voltage 90 times 17 times 17, repeat that twice, yada yada. So the original pulse sequence was quite long, but here's what I did. I took the final voltage that was going to be applied to it, A0, and then the final amount of time, 0E, and I'm only going to repeat it once. So basically, I truncated the lookup tables just using the last value from each waveform. This makes sense because the last thing that the waveform does is sets the pixel to the proper value, or to the proper color. So what this thing is doing is, let's say you want to go white to white, it's actually first converting it to black, then converting it to white, then to black, then to white again. But that's very messy looking, and if we're trying to do a quick update, that's no good. So we just go straight to white, and if the pixel was already white to begin with, we just make it white again, no problem. And so you'll see that that's true for all of these things. The original black to white LUT looked like this, and again, I just cut the last bit out of it. Let's see if we can actually probe those voltages to bring this thing full circle and see if our code is actually working the way we think it is. So you'll see here I've cut away the encapsulant. There was actually a polymer that was covering up this whole area on here. And this long bit of silicon is actually the driver chip that is doing the work of converting our serial commands into this giant matrix scanned pixel array that is the display itself. You'll see the abbreviation COG, which is chip on glass, which is that long piece of silicon, the actual driver chip. Another little gotcha is that the glass itself has a lot of wiring on here, but the wiring is all covered with a very hard insulating layer, some kind of oxide. So if you just take even if you take a relatively sharp steel probe and just touch down on the surface here, you can't access any of the electrical signals in there because the steel isn't hard enough to cut through it. Instead, what we have to do is use a tungsten carbide scriber and cut away the top oxide layer and then get a probe down on there. So I'm going to zoom in even further and see if you can see this. Here's a closer view, and if you look carefully, you can even see they were nice enough to leave us some test pads on here, and that one even says COM, so that's probably VCOM. And then a little bit lower you can see here where I scratched away the coating, and believe it or not, this actually works pretty well. You would think if you scratched away the top oxide layer, it would blow away the conductive layer underneath. But as it turns out, you can put a probe here and it actually has pretty good conductivity. So let's move over to the side of the display and you can see where I'm going to get the individual pixel lines. This is the edge of the display, and if you look closely you can see this honeycomb structure. Those are actually not pixels, those are just the cups that contain these colored particles. And so the actual pixels can be independent from this sort of cup structure. And then here's a little bit where I've cut away the encapsulant very carefully, and I'm going to go in there and scratch it with this scriber and then try to get a probe on there. I forgot, or I wasn't thinking, that this is actually an active matrix of transistors in there. So the row and column inputs are scanned, and so seeing any sort of meaningful waveform from there is very difficult because it's spread out across all the pixels. And so I guess we could change the entire display, but I was having trouble probing. So just based on this diagram here, it's much easier to measure VCOM. So let's take a look at the scope now and measure VCOM, since it's much easier. And then we'll alter the lookup table and see the effect it has. One of the neat features of this new oscilloscope is that it has 8 channels that can be configured as digital or analog on each one. So when it's digital, you get 8 digital inputs. You could actually have 8 by 8 digital inputs, or you could have all 8 analog inputs, or some combination thereof. So today I have 8 digital inputs here, and we're keeping track of the SPI bus, plus this data command thing, reset, and the busy flag from the display. And then I have channel 1 reading VCOM. So I'll just tack onto here and then run the program. And hopefully you'll be able to see the display updating back there. And we should see VCOM change into something else. Let's see if it shows up. Okay, and there it is. So VCOM is 10 volts or 11 volts for a while, and then it's 0, and then it's back to 10, 0, and 10 again. And if we look at the LUT, we can see that makes sense because the final line of the LUT has starts with hex 40 and ends with hex 2, which means repeat twice. And 40 corresponds to this higher VCOM voltage. So I'll put this back to 0 and save the LUT and then run the demo again. You can see, interesting, the display still works, which is interesting. You would think just making a random change like that would completely destroy it, but actually it's still okay. And then it went away. So since we updated the LUT table to be zeroed at the beginning, this thing just stays at ground the whole time. Let's finish off by going back to the digital and seeing how fast the frame rate is on my hacked firmware version. So I'm going to turn off channel 1 since we don't need the analog, and I'm going to change the trigger to, instead of triggering on channel 1, we're going to trigger on channel 6. And since 6 is a digital, it breaks out all the different pins in there. So D0 is the serial clock. It'll just start triggering right away. The record length is super long, 125 million points, and the sample rate is 62.5 million samples per second, so we should get 2 seconds worth of data here, which would be plenty. I'm going to run the code, and I'm going to stop it, and when the code gets to the part where it's doing the rapid frame update, I'm going to do a single acquisition. So I'm watching the display, and now's a good time, so I'll hit it. It triggers very quickly, and then 2 seconds later we should be able to see all the data there. Okay, cool. So this is each frame being updated. So if we wanted to know what the frame rate was, we could use the cursors and just get a real quick idea. So from the end of that one to the end of this guy is 374 milliseconds, 2.7 hertz. And so that's about the frame rate that I was getting. Now we can make it even faster. Since we have control over the waveform, we can make it, almost nothing. The problem is the display will have very poor contrast, and so it takes time for those charged particles to rise to the surface. We can also take a look at, you can see that, so this chunkiness here, this is how long it takes the microcontroller to actually send the frame to the display, and then this is the time it takes the display to actually show it. So if we look at this thing a little more carefully here, we can zoom in on it. So then looking at the zoomed in section, I'll use the cursors to measure the time it takes to actually send the stuff to the display. Roll in here, so 24 milliseconds out of the, what did I say, 200 or 300 or whatever it was, is actually taken up just by the SPI bus. And in fact, we're cranking really fast. It's doing about 14 megahertz is what this thing is measuring here. I think it's actually a little bit higher. It's closer to about 18 megahertz. See if we can zoom in on that. Zoom way in, even at 62.5 million samples per second, it's actually hard to see exactly what's going on. We'll bring in the cursors again. And this clock edge, it's like 20 megahertz. It's somewhere between 14 and 18 megahertz clock. If you look at this, the data being sent has a lot of dead time in between, and it's partially because the chip select line has to toggle. Anyway, it's getting kind of detailed, but this scope does make it quite easy to see what's going on. In addition, it's decoded the entire set of data and has it available in sort of a bus form like this. Another cool feature is that if you know what you're looking for, you can search through all the data. So for example, I have this search already set up, and it's looking for hex 20. Hex 20 happens to be the code that sets the VCOM LUT. So we can use the navigate buttons and then jump through the data and find all of those 20 hexes. So if we zoom out a little bit, we can see what it's setting the VCOM table to be. So 20, and it even has this, this drag zoom, which is pretty cool too. Okay, see you next time. Bye.